Electrical diagnosis and repair for the GMC Motorhome service technician. We're going to talk about diagnosis and correction of several common problems that have occurred, and also how to avoid some electrical problems. Let's begin with the 12-volt system, including the power converter, the battery, wiring harnesses, and heater air conditioning circuitry. Before discussing diagnosis of the power converter, let's review some facts about its operating characteristics and what it does and doesn't do. Primarily, the converter powers the living area 12-volt system from a 120-volt power source. Secondarily, the converter will charge the living area battery when there is no other load, or if there is a moderate load. In a no-load condition, it puts out about 14 volts, which will charge a battery. As loads are added, however, the voltage drops, and may get low enough so it won't charge the battery at all. And if more than 45 amps are being drawn, the total capacity of the converter, the living area battery may supply part of the draw and will discharge. Also, on early models, 1973 and 74, with the living area battery up front, the converter will not charge the chassis battery unless the battery boost switch is in boost, and there's enough power to energize the magnetic switch. And it will not charge the motor generator battery on early models unless the third wire modification has been made to put the generator battery in parallel with the living area battery. Thus, the customer should not expect more from the converter than it is designed to do, and should consider the chassis 80-amp alternator the primary battery charging device for both the chassis and living area batteries. Likewise, a discharged living area battery does not necessarily indicate a converter problem. Now, a quick way to determine if there is a converter problem is to refer to the voltmeter on the monitor panel. Suppose with the engine off and no load on the 12-volt system, the meter reads in about 12 volts or less, when the converter should be putting out 14 volts. Then you start the engine, and with the engine on, the alternator begins to generate. The voltage jumps up to about 13.5 or 14 volts. These conditions indicate a possible converter problem. A common cause of such problems is simply a poor ground on the frame channel behind the converter. The screw may be loose, or the electrical contact poor due to high resistance, and the ground connection is in a difficult place to reach. A simple fix is to splice an added length of wire to the ground lead and ground it in a more accessible location, such as behind the kitchen cabinets. Incidentally, the better the ground, the better the converter will perform. Also, check the frequency of the 120-volt input. Testing at the motor generator output terminal, the frequency meter should read 59 to 63 Hertz at 110 to 126 volts. If the frequency is less than 60 Hertz, the converter output voltage starts to fall off. Also, when testing the converter with shop power, plug in your frequency meter and be sure your source is 60 Hertz or more. For in-vehicle testing of the converter, disconnect the living area battery, plug the converter into a known good 120-volt source, and turn on any living area 12-volt light to load the converter slightly. A slight load is important for a good test. Measure the output with an accurate voltmeter. If it is between 13 and 15 volts, the converter is okay. On the bench, you can test the converter by connecting a 100-ohm resistor with a 1-watt capacity and a 1,000 microfarad condenser with 15-volt DC in parallel across the leads. This will provide the best load for an accurate test. Plug the converter into a good power source and check for a 13 to 15-volt output. If the converter tests okay either way, any 12-volt problem in the living area has another cause. If you find very low voltage output, the converter probably has a shorted or open diode. You can easily find out by disconnecting the power source and making a continuity check across the leads with an ohmmeter or self-powered test light. testing one way and then reversing the leads. If there's no continuity either way, or continuity both ways, it means a bad diode. Do not attempt to repair the converter locally for this problem. The diodes are matched for a balanced output, and replacing one is asking for a repeat failure. Instead, contact GMC or the converter manufacturer. Rebuilt converters are available on a 5-day turnaround for about 40% of a new converter cost, so you can save the customer some money if the unit is out of warranty. One final point about the power converter. Humming noise is not an indication of a failure. It can be reduced or eliminated by installing pads under the mounts. Refer to Bulletin 75-TM-14 for this information. Now let's talk about batteries, and again begin with what to expect from a battery. First, except for Freedom batteries, expect to use some water. This is especially true of the living area battery cycling between discharging and charging. Second, expect the rear battery to discharge whenever the living area 12-volt load exceeds the converter output, or whenever it stands idle. Especially expect it to discharge if the top is dirty, since this creates a high resistance path for electrical flow between the terminals. You can prove this by measuring a definite voltage between the positive terminal and the top of a dirty case. Third, expect it to not function properly and even to fail early if not properly maintained. For example, charging causes an acid to discharge that corrodes terminals, causing a high resistance condition and reducing the net voltage output. To maintain the rear battery properly, keep it filled with water to the top of the ring in each cell and check it frequently. Failure to keep it filled can mean lower voltage and shorten the battery's life. Keep the terminals clean. Use appropriate wire brushes to clean corrosion from the contact surfaces, and then tighten the terminal connectors to specifications. Use a good terminal coating to coat the terminals. The coating helps protect them from acid and also won't melt and run into the case as grease or petroleum jelly will. Keep the case clean. Periodically wash off corrosion with baking soda water and wipe off all grease and dirt. Also, be sure the hold down is secure so the battery won't bump around and get damaged. When the vehicle is sitting for an extended period, maintain a surface charge by keeping the power converter plugged in. Besides the convenience of having the battery charged if needed, this prevents the water from freezing and extends the battery life by reducing cycling. Performing the maintenance procedures just mentioned will often correct an apparent battery failure. However, even the best maintained battery has a service life limit and eventually must be replaced when it will no longer take or hold a charge. There are several battery tests with which you're all familiar and can review in the maintenance manual if necessary. Here, though, is an important point. If the battery tests bad, replace it. However, sometimes a battery will test good and still won't hold a charge. In that case, test for a drain-down, high-resistance short to ground with an ammeter or 12-volt test light in series with a positive terminal and cable, and all loads turned off. If the test light glows dimly, or the ammeter shows current draw, locate and correct the short to ground. If there is no short, install a new battery. Just a brief word about the maintenance-free Freedom battery used on late-model motorhomes. The charge indicator, which is an hydrometer built into one cell, should be checked regularly. Checking procedures for the Freedom battery have been covered in an earlier slide film, and there is adequate reference in the maintenance manual and service bulletins. Just follow the instructions if a test seems required. In the slide film Electrical Diagnosis Tools, MH-24, we demonstrated how to test the dual-diode battery isolator with an ohmmeter. It can also be tested with a self-powered test lamp. Remember that the battery isolator is used merely to be certain the living area 12-volt system doesn't drain the chassis battery, and it can be bypassed if necessary without any harm. For instance, if either diode is open, the alternator will not charge its battery. A temporary fix is simply to jump the two battery terminals across the dead diode with a number 10 wire. Just don't forget that this ties the two 12-volt systems together, so both batteries could be drained by the living area system. The jumper should be removed with the vehicle parked, and the diode replaced as soon as possible. Another reminder, if the chassis battery is dead, the engine can be cranked from the living area battery by holding the battery boost switch in the boost position while operating the starter. And in case of a problem with the Delcatron generator, jumping the isolator will permit the power converter to charge the chassis battery, provided it has no other load to handle. Next, diagnosis of wiring problems. Don't forget that the wiring diagrams in the back of the maintenance manual identifies all the wires by size and color code, and also identifies connectors and their locations. In troubleshooting open or high-resistance circuits, always test for power into and out of the connector whenever possible, since many open or high-resistance conditions are at the connector rather than the result of a break in the wiring. However, when there's power at one connector in a circuit and not at the next, you can test along the wire by pushing the probe tip through the insulation and thereby isolate exactly where it's open. Now here's a tip about using the 12-volt test light. When you attach the ground clip to aluminum, an oxide coating on the aluminum can prevent it from grounding, and you might think the tester isn't working or the circuit isn't hot where you're testing. So if there's no iron handy to ground the test light, scratch the surface of the aluminum to be sure you get a good electrical contact. A specific open circuit problem that you should be aware of is failure of the chassis air conditioning blower to operate on the high blower setting only. The usual cause is an open inline fuse that feeds the blower motor full voltage when the blower relay is energized in the high position of the switch. To diagnose it, open the right-hand access door, locate the fuse holder, and test for power in and out. If power in is okay, but there's no power out, the fuse is open. And usually it opens because of a resistive melt condition due to the exposure of the fuse holder in front of the radiator. Rather than replacing the fuse or fuse holder, it's recommended that you substitute a 30-amp fusible link for the fuse holder. You can get the link at any automotive parts store, or order a repair kit, part number 888-5540 from GMC. Of course, if the problem persists, say the fusible link blows, you would test for an overload in the circuit, either high blower motor current draw or a short to ground in the feed. Let's switch our attention now from the 12-volt DC to the 120-volt AC system. We mentioned earlier that the power converter is sensitive to the AC voltage frequency. Most 120-volt components are sensitive to low voltage, particularly the roof air conditioner and refrigerator. The Sol Air furnace will not run on low voltage. The blower will go on momentarily when the thermostat contacts close, but in a few seconds it will stop. Here's why. When the furnace first starts up, the blower has to get up to speed in order to close the contacts on a centrifugal switch, which opens the gas valve by energizing a solenoid. The thermal relay heater is de-energized when the fan switch is energized. But if the voltage is low, the gas won't come on, and in a few seconds the thermal relay will pop the reset and shut everything down. So, if the blower comes on momentarily but the furnace doesn't fire, always check the voltage source first. With roof air conditioning, low voltage can cause on-off operation and can destroy the compressor motor. A compressor motor that has too little voltage available will strain to operate on the low voltage. In other words, it becomes overloaded and current draw increases. The overloaded circuit breaker may protect the motor initially by opening the circuit. However, it resets when it cools and the motor strains to run again. If the compressor motor is still okay when you get it, check the unit with a known good 120 volt to see if low voltage is the only problem. Remember, there has to be at least 110 volts at the overload terminal of the compressor and through the overload to the compressor O terminal. If there isn't, troubleshoot the electrical system as described in the maintenance manual. Then, where low voltage has caused the problem, explain to the customer about keeping the motor generator properly tuned up, about voltage losses in extension cords that are too long or not heavy enough, and about checking for voltage before turning on the air conditioning. A couple of signs of voltage problems are an extension cord that heats up, or lights or TV going dim when 120-volt equipment is turned on. The smart motor homeowner will test the power in at the campsite with his own inexpensive voltmeter before he tries to run the roof air conditioner or the furnace. Now let's talk about some tips on diagnosis of the electric refrigerator. The refrigerator has two power sources through the inverter transformer assembly, either 12 volts DC or 120 volts AC, and an automatic switching device to select one or the other. If the 120 volt source is off, or the voltage is too low, the inverter changes the 12 volts DC to AC. On the 7.5 cubic foot refrigerator, the transformer boosts it to about 23 volts AC to operate the compressor motor. On the 6 cubic foot model, it is boosted to 20 volts AC. When the AC source is supplying 90 volts or more, the switching device, called a voltage selection relay, takes the inverter out of the circuit, and the transformer reduces the input voltage to 23 or 20 volts AC, depending on the refrigerator model, to operate the compressor motor. Voltage checks at the compressor motor power terminal are a good starting point in problem diagnosis to check the power supply and the inverter switching device. With the 120 volt AC unplugged and operating on DC, measure the voltage with an AC voltmeter. Remember that on DC operation on the 7.5 cubic foot refrigerator, the meter will read between 31.5 and 33.5 volts, even though the actual voltage is 23 volts. On the 6 cubic foot model, it will read 27.2 to 29.2 volts AC. This is because of peculiar output characteristics of the inverter. Then, leaving the 12-volt source connected, plug in the refrigerator 120-volt power cord to a known good source. On 120-volt AC operation, the meter should read 22 to 24 volts for the 7.5 cubic foot model and 19 to 21 volts for the 6 cubic foot model. If the two readings are okay, the power supply and switching device are all right. Another useful test is to measure current draw by snapping an amp probe on the compressor motor supply wire and checking for 2.6 amps current draw for the 7.5 cubic foot model and 2 amps for the 6 cubic foot model in both 12 volt and 120 volt operation. If the current draw is to spec both ways, the switching device and compressor are okay. If draw is okay in one operating mode and not in the other, there's a problem in the inverter assembly. And if draw is high or low both ways, the refrigerant charge is wrong and the refrigeration system must be serviced. In case of an inverter assembly problem, the inverter and the transformer are now replaceable individually. You do not have to replace the entire assembly. Here's how to test which part is at fault with an ohmmeter or a self-powered test light. First, disconnect both the 120-volt and 12-volt power connectors and the connector to the thermostat and compressor motor. And check the gray thermostat leads for continuity to be sure the problem isn't just the thermostat or its wiring. The transformer should be tested first, both the primary and secondary windings. We're showing the test on the bench for convenience, but it can be done on the vehicle. Test the secondary windings at the blue and yellow transformer leads of the thermostat connector. There should be continuity through the windings with a very slight resistance, perhaps 3/4 of an ohm. Test the primary windings by opening the inverter to transformer connector and measuring resistance between the white and white-green wires. The winding resistance should be about 12 ohms. Also, touch one of the ohmmeter leads to the mounting plate to test for grounding. There should be no continuity. Test the inverter with the transformer connector hooked up and a jumper wire across the terminals of the gray thermostat wires. Measure the resistance between the 12-volt leads to the inverter. It should be about 35 ohms, but can be between 4 ohms and 60 ohms, and the inverter still good. The test procedures we've just summarized for the refrigerator are detailed in Bulletin 76 IM1 and 76 TM2, and in the maintenance manual. One final point. Some older inverters may have a chattering condition during the DC-AC switchover. An anti-chatter device can be installed to prevent this. Remember that electrical diagnosis and repair are often very simple if you use the right tools and follow the approved procedures. That's the right way to keep your customers satisfied with their GMC motorhomes.